Okay, so today, the phase-sensitive detection. So what we talked about last time was what is the nature of the signal that we're recording fundamentally. Each data point, we record lots of data points, but each data point consists of the vector sum of the XY magnetization across the brain. So at each point there's the magnetization in the XY plane is pointing in some direction. So if this is the bore, the magnetization will be pointing somewhere around the XY plane, perpendicular to the bore. And at each point in the brain, there's some vector of some angle and length. It doesn't have to be the same length, different lengths, different places. And what is the fundamental signal that you record that forms the basis of MRI or spectroscopy, same. And what it is the vector sum of all those local magnetizations added together to give you one vector, one 2D vector. And that's the fundamental sort of data point. And so we fiddled with some equations to try to describe why that's what the signal is, but we didn't say how do you actually record that? And it turns out you can record that single data point at a single time point just with one coil. You only need one coil to do it. So what we want to talk about today is how it's actually done. And it's a pretty simple thing. It involves a trigonometric identity, which I learned somewhere in 10th grade and promptly completely forgot after that. But here's a use for one. And so what's the input? So our input is some coil, and I haven't been drawing the capacitor in a coil. Coils always have a capacitor in them. And the reason for that is that you might wonder, a capacitor looks like a gap in the coil, and it is. But what a capacitor can do is it can build up charges of either sign on the plates. For a while, it can hold a certain amount of charge. And so the reason you put a capacitor in a coil is because you want the coil to just pick up the main resonant frequency. You don't want it to pick up other frequencies. And so if you size the capacitor, make the capacity of the capacitor correctly, what will happen is that will be perfect to allow current to oscillate back and forth in the coil. It looks like it's going through the capacitor, but it's not. What's happening is the charges are building up on one plate up to the sort of capacity of the capacitor, and then as the sinusoid goes the other direction, the charges will build up on the opposite plate. And any frequency that's not the one that is tuned to the capacitor won't be able to do that, because the capacitor has the wrong sort of capacity for that oscillation. And so you always have a capacitor or a couple capacitors in a coil, but that's the reason they're in there, so that they'll tune the coil to the particular frequency of the resonant frequency of the protons without, and so ignore other frequencies. So then I put the capacitor in this time. I didn't put it in last time. So that's our coil. And so we just get one stream of numbers out of there. At each point in time, there's just a voltage coming out of the coil. And so how do you process this? So here's that voltage coming out of the coil, sort of voltage at time t coming out of the coil. So that's just a number. That's not a vector. And so that basically is going up. It's going up to that voltage there. So what do you do then with that voltage? So you put it into the phase-sensitive detection unit, and what is the phase-sensitive detection unit? It's basically just multiplies. Now, when you hear that, you might think, multiply. How do you sort of multiply with current? And so a very simple multiplier is a transistor. And so a transistor, it has two inputs and one output. And the way a transistor works, you can sort of think of it as a simple multiplier. So say you have a big current being supplied to one of the inputs here, and here's the output. This other current here serves as the control current. And so what does that mean? It means the amount of this current will multiply the big current. That's fundamentally what a transistor does. That's what an amplifier does. So if you want to amplify a signal, you just take a continuous big supply, and then you have this little gate here that can multiply it by a number. That's really what it's doing. It's just multiplying by like 0.5, and so then the output will be 0.5, whereas if it multiplies by 0.01, then the output is 0.01. It'll be larger. Say you have 100 input here, and you multiply it by a small number, and then you'll get like 50 or 1. So that's fundamentally how you electrically multiply something. This isn't a general purpose multiplier. This is just multiplying by one factor as opposed to being able to change both. But whatever, you get the idea. So that's how you actually do a multiplication with in an electrical circuit. But what are we multiplying by? So we're multiplying by a reference signal. So we're multiplying by a reference signal. And so what is that reference signal? So that reference signal is the RF transmitter oscillator. So what does the RF transmitter do? Well, it just generates a 123 megahertz sine wave. It just generates a very accurate 128 megahertz sine wave, just one frequency. It just makes one single frequency. You can change what the frequency is, and you can change how loud the frequency is, but it's basically at any point in time, it just makes one frequency. So that's how the RF transmitter works. It's just a single frequency. And so we feed that. And so the transmitter is what defines where t equals 0 is, because the protons are oscillating around, and we said we could sort of measure the angle of the protons at any point in time. Well, what does that mean? It has to be angle relative to something. So what is 0? What defines angle equals 0? The transmitter defines what angle equals 0 is. And the transmitter is very accurate, and so it can do 123 million cycles per second, for 20 seconds, billions of cycles, and not get off. So, later on, a couple seconds later, the transmitter will still be exactly hitting the cycles. And so so the transmitter basically defines, t equals 0. It sort of sets the coordinate system for everything, for receiving. Because remember, this is a receiving signal. So the transmitter would have done something in order to generate a signal in the brain, and then the signal is coming back out, but the transmitter oscillator is still running. And we take that transmitter oscillator signal and multiply it by the signal that we get back from the coil. And then what do? So we send it to a low-pass filter. And so what's a low-pass filter? Low-pass filter just means, let low things through. And then we get a signal. So we get a signal. And this is still just a real signal. It's just a number. So it's a signal, we'll call it the real component of our recorded signal at a time point. And so when you look at this, it's just kind of like, what's actually going on here? So this is one of our phase-sensitive detection units. So this is a, PSD unit. And this is very old technology. This is like an old radio technology from, 80 years ago. These are not new ideas. So what do you get out? So what you get out is called Sometimes it's called, the demodulated signal. If you ever read any, so this is the demodulated signal because it's kind of not going as fast. Or sometimes it's called the baseband, which, if you read that, a baseband, what the heck does that mean? It's old radio technology. But we know it as the rotating coordinate system, because this is the rotating coordinate system. Too many coordinate systems. This is actually, this is our signal basically is that we record is a signal in the rotating coordinate system. It's really just the phase of this oscillation. Like what is the angle of the oscillation relative to time t equals 0 as defined by the transmitter. So these are all sort of names for the same thing. So how does this work? So what we're feeding in. So we're feeding in our reference signal is, let's say it's a cosine. So it's a cosine of the center frequency of the transmitter, which is supposed, you can change it, but the idea is you want to somehow set it to whatever the resonant frequency is at 3 Tesla. And remember, that's a frequency, that's radians per second. This guy is seconds, so you multiply that and you get radians. You get an angle because you want to take a cosine of an angle. And so that's what we're feeding in. So we're feeding in a cosine as our reference signal. And so what does that do? So now we have to do a trigonometric identity. So basically this signal here, this signal is proportional to, because there's going to be some factor, like there's going to be some fixed factor that will tell you what the exact voltage is. So it's just proportional to what we're going to write over here. So it's proportional to the RF signal times the reference signal. But it turns out when you do this multiplication, you're going to get several frequencies out of it. You're actually going to get 2 frequencies out of it. And so to understand that, let's write down. Let's just say our it was a cosine. So yeah, I had written it in my. Should I do it as the way I did it in my notes? So in my notes, I wrote it as the sine. I wrote our reference. Oh no, I got it there. Okay. So if we have, say, our incoming signal was something like a sine. So we have a sine of our incoming signal, and our signal might not be exactly the same frequency as the transmitter signal because it's the brain. You tried to line everything up, but maybe it's a different frequency, or maybe you just changed the frequency of the transmitter and on purpose did it slightly off. That happens too. And so you're going to have something that's close to the center frequency, and there's going to be some offset. It's not going to be exactly the same frequency. Your brain oscillations are not going to be exactly the same frequency as the transmitter. And that thing is so those 2 frequencies are added and multiplied by time in order to get an angle. And then we're multiplying by this reference signal. And so in my notes, I put down sine. I put cosine here just because I like to put cosine before sine, but I'll just leave it the same as the notes. So we're multiplying by a sine here, and that's just the center frequency. Okay, so that's what we're doing sort of mathematically here. Taking our signal, which doesn't necessarily have to be the same frequency as the transmitter, and we're just simply multiplying it by a sine or a cosine. So So how do we simplify this thing? And so for this thing, we need a trigonometric identity. And so for the one for sine times sine looks like this. So the sine of angle A times the sine of angle B equals 1/2 the cosine of A minus B minus the cosine of A plus B. So I remember doing these problems, kind of like, what could you possibly use this for? So here's something to actually use it for. So what is A and B? So the idea is that we take this thing. So this thing is an angle. So that's our A. And then this thing over here is our B. And so if we do that, you can see that so this thing turns into cosine of A minus B. And what is cosine of A, that A angle minus B? Well, it's going to subtract out the omega 0 term, and you'll just end up with the delta. And then you subtract off of that A plus B. And what's A plus B? It's going to be 2 times the omega, because you got 2 copies of it now, plus the offset frequency. So what is that, using that, what does it boil down to? So it boils down to 1/2, which we can ignore because it's just kind of a constant factor, of the cosine of the offset frequency. The cosine of the offset frequency times time minus the cosine of 2 times the center frequency plus the offset. That whole thing times time to turn it into an angle. And with another, there we go. So what is, how can we, if we just draw that out in frequency, what does it look like? So it looks like if we have a signal, so here's our sig, and this is frequency going in this direction. So here's our signal. It's a pretty high signal, 123.01 megahertz. And then we've got a reference, and the reference doesn't have to be exactly the same as the signal. Let's make it just a little bit lower than the signal, so it's slightly lower than the signal. So this is our omega 0 reference, omega 0. And so then what is our output? Our output is basically the difference between them. That's the delta omega. So it's this difference right here. Put that difference in. So here's the diff. That guy's the delta. So it's the difference between them plus 2 times. So this guy is 2 times the center frequency plus the difference. So this is the output. But then we send it through a low-pass filter. And so the low-pass filter means like just let through the low one and erase that one. So get rid of that guy. So this is the filter. So that's sort of a graphical way of writing out what we just did in the equation here. So basically you will, by multiplying by a single frequency of a sine or a cosine, there's another trigonometric identity for, multiplying a sine times a cosine noise. Put that one in there. So if we take sine of A times cosine of B, that equals, 1/2 sine A minus B plus sine A plus B. So that's another, that's how we would, okay, these are trig ident. So, because we're going to need that because we're going to multiply by a sign down here. So I kind of, the example I worked here was for the second part of the phase-sensitive detection. Okay, so this is just one piece of the phase-sensitive detection, and so how do you get that second signal out of the coil in order to be able to make a complex number? Basically, we've got to take that same voltage, so just make a copy of the voltage, just branch off a wire, and so that exact same voltage will be now run through another phase-sensitive detection, and that phase-sensitive detection will multiply by a cosine, by a sine instead of a cosine. And that one will be filtered out also. The high frequency part will be filtered out. And out of that, we'll get our imaginary signal. Now, it's not imaginary. It's a real signal, just as real as the other one. But this will essentially allow us, so here's, so this is, reference signal 1, and this is reference signal 2. And so where do you get the reference signal 2? Well, it's just whatever the transmitter was doing delayed by 1/4 of a cycle. So you can sort of electrically delay the transmitter signal to turn it from a cosine into a sine. So basically we just do exactly the same thing, multiply it by another sinusoid, filter out the 2 times frequency component, and so that we just end up with the low frequency component. So this fundamentally, this is the actual sort of physical realization of how you get that signal that we talked about last time. So last time what did we say, the signal was? We said this, this signal that comes out of the head at a time point, just at a single time point, is a complex valued signal that is basically the amount of XY magnetization. That's just an amount, not a vector. And then it was multiplied by this E business. So, e to the minus I offset frequency times time. So the offset frequency, this sort of difference in frequency, is really the phase of that oscillation. And what does the phase mean? It just means like the angle of the oscillation at a particular point in time relative to angle 0 as defined by the transmitter. And the only difference down here, so this is RF transmitter with 1/4 cycle delay. And so this guy will be a sine, which is the one that I worked out there. So that's how we actually, this is the physical realization of how we actually get this. We only need one coil to do it. And so we've essentially sort of generated a second signal. And what is the second signal? This is kind of the X and the Y component of that oscillation. The X and the Y component of the phase of the oscillation. So that phase is changing every instant. So over time, the phase is going to be a little bit different, because if the oscillation in the brain was a little bit faster than the transmitter oscillation, every cycle is going to get further ahead. And so this phase is kind of a dynamic thing, and it's constantly changing, over time. So it's changing too. It's not changing anywhere near as fast, and so that's why it's demodulated. But it's changing. At a point in time, it's a single fixed number, but the next tiny fraction of time, it's going to be a different number. And so what does that look like? So if we just take this single voltage that's coming out of the coil, so here's that single voltage that's coming out of the coil. So what does that look like? Well, it's got a gazillion oscillations. I can't, draw anywhere near enough. There's 123 million. So this is our estimate of 123 million oscillations per second coming out. And it's falling off by, e to the minus t over t2, of course, the amplitude of it. But that's a single number. That's just voltage at time t. And so what do we do when we sort of run it through this phase-sensitive detection? We turn it into two voltages. And what do those look like? Well, they're going to have, a couple different frequencies in them. They'll have the same envelope, but they'll be changing a lot more slowly. And so, let's just draw some random thing in there. So there'll be some signal which is basically representing the phase of the oscillation, how the phase of the oscillation changes over time. That's what this is, actually. This is because it's not measuring the, this vector here is not representing the 123 megahertz oscillation. It's just representing how the phase is changing over time. That's what this one is. And remember, once again, this guy's just a number. That's an amount. And you're multiplied by a complex number. So this is complex number of where the amplitude equals 1. So the amplitude of that vector equals 1. You scale it by a number here. And so when you multiply a scalar, a real number, times a complex number, you get another complex number. So this guy's complex again. But it got scaled by the amount of the magnetization at this angle. So say this one is our real signal. What's going to happen, you're going to get another signal coming out of there, which will be, it will be sort of offset. Oops, went the wrong way on that one. It will be sort of offset in phase. I'm not doing a good job of getting the phase, but it doesn't matter. Okay, so you're going to get two numbers at each point here. And what do those two numbers represent? Let's just take, just a concrete example. So it's a complex number. So let's take an example of, say, like this point in time. So say right at that point in time, we've got that much for the imaginary and that much for the real. So what does that what does that look like over here? It's a reasonably good number. It's a big number for the real and a smaller number for the imaginary. So that's going to be that number. So that's our example A. And then if we go at some later point in time, let's pick another later point in time. Say we've got, this point in time right here. So that's point B. So that point B is going to have a positive number, a smaller positive number, and then it's going to have a negative imaginary number. So here's the imaginary axis. So it's going to have a negative imaginary axis. So that guy looks like that. So this guy is A. This guy is B. So at any point, so it's a dynamic signal, it's constantly changing over time, but the rate of change is a lot less than the rate of change of the very rapidly oscillating signal. So this is the actual sort of simple underlying mechanism by which you get the rotating coordinate system, which measures the phase of this oscillation rather than the actual oscillation itself. And it's very straightforward. You just take this exact same signal from one coil, and you multiply it by a cosine and then multiply it by a sine, and then just filter out that high frequency part, and then you end up with the phase. It's sort of amazingly simple. And but like I said, if you don't understand this, then you can't. The whole thing is about this complex valued signal. And so how do you get a complex valued signal? You know, we're essentially adding some information because we're adding this reference signal in there, and that's what allows us to sort of get that second number out of a single stream of numbers coming in, single stream of voltages coming in. Okay, so let's just stop for a second, ask for questions. I went over this slowly, so hopefully it was reasonably understandable. So at each moment in time, you have these two numbers, and these two numbers represent the summed phase, which you can also just think of it as the summed instantaneous direction of the XY magnetization at a point in time, and summed across the whole head. So there's no spatial signal here. It's just like we just summed across the whole head. So every data point comes from the whole head. Okay, there's got to be a question or two. Completely clear? What, question? Yeah. Yeah. It will be off. It will be in general off by. It depends on the frequencies that it contains, but in general, I didn't do a good job, but it should be off by about a quarter of a cycle. Yeah, the real and the imaginary one. Yeah, and if you came to the Friday 8 a.m. lecture, all this technology, like the phase-sensitive detection, the chemists already were doing this like in 1960. So this is not a new thing. This is just a basic way that you collect spectroscopy data. So this was not a new thing. This was just adopted for MRI. It was already there. And like I said, it was something that came from 50 years before that, because they were already doing this for FM radios. They had circuits that do this kind of multiplication in there as a standard piece of hardware for demodulating a signal that's coming over the FM radio waves. Okay, so when you first hear about this, it's the part that's kind of a little hard to get your head around is like the phase. What does the phase mean? How could you record the phase of a signal? But what is the phase? The phase is just kind of the instantaneous angle of the magnetization. And over time, that's going to be changing. It won't be changing anywhere near as fast as this 123 megahertz. This signal is typically, this is what is digitized, but you don't have to digitize it at such a high frequency. So you only need like about maybe 100 kilohertz. The kilohertz. There we go. So the 100 megahertz, that's 100 times, at least, like 1,000 times more cycles than you get out of the signal that you actually use in your image reconstruction. So you don't have to digitize it at this really high rate. Although technology has changed, cell phones now can just digitize at gigahertz frequencies. That used to be really expensive, but now it's just sort of cheapo. But still, this is the way scanners work, even when they're digitizing at very high frequencies. Okay, so any questions about phase-sensitive detection? So this is phase-sensitive detection unit 1. This is phase-sensitive detection unit 2. And that's how we get our, so these guys, that's the X and the Y component of that right down there. That is our signal in the rotating coordinate system. So it's just the movement of the XY magnetization that is relative to the center frequency from the transmitter, the difference from the center frequency from the transmitter. So it could either be positive or negative. I drew it out here as if the frequency coming out of the head was a higher frequency than the transmitter, but it could be the other way too. It just depends on what you did with your transmitter or what the brain did with the signal. Or what the gradients did with the signal, because the gradients will mess with the oscillation frequency. That's the point of gradients, to sort of change the oscillation frequency of stuff in the brain. Okay, all good. So now, I just want to talk a little bit about signal to noise, because this is kind of a practical consideration. Like if you're trying to record some MRI data, one of the things you have to be concerned about is, do we have enough signal to work with? And one of the things that affects the signal to noise is how big of a voxel. We haven't said how you determine a voxel, but if you make a smaller voxel, your image will look a lot more noisy than if you make a bigger voxel. But there's also big effects by where you put the coil. So if you put the coil closer to the head, you get a bigger signal. And you have different sizes of coils that could affect things. And so what are some of the sort of practical considerations about signal to noise? And I'll start off with, I remember when the physicist told me about this, I sort of had a somewhat weak grip on the concepts, and the physicist told me this, and I said, what? Is that really true? So you often have more than one coil. So we talked about if you put a coil, say, if you put a coil vertically versus a horizontal coil, those will be off by 1/4 of a cycle. And so you might think, well, why do you mess with all the phase-sensitive detection? Why don't you just put coils in different places? That's another way of collecting a second signal that gives you the other component of this two-dimensional phase of the oscillation. So if you have a vertical coil, so here's a vertical coil, capacitor in it. But you could also put a horizontal coil, like on the top of the head, like this. And so that guy would get rid of the need for the phase-sensitive detection, because that one would. But you can immediately see the problem is going to be, well, what if it wasn't exactly at the top of the head? Or what if you put a third coil that was somewhere else? But there are coils that are set up this way. A good example would be what's called a birdcage coil. And so back in the day, this was like the standard kind of coil that you used. And it's got some capacitors in it this way, and it's all hooked up. And understanding how it works is a little tricky, because the current is oscillating around in different directions inside each of these little sub-loops, and they're all connected up. They're all connected up in a loop like that. So you can immediately see, that looks a little complicated, trying to figure out what's going on there. But if I feed in a cosine here, and I feed in a sine that's nearer the top of the coil, that's kind of like a quarter of the way around the coil. A coil like this will make a very nice rotating magnetic field in order to stimulate your protons to be aligned with each other, or equivalently to actually pick up some protons that are rotating. So this one is called a birdcage coil. And coils like this are still used, similar to this, are still used for the body RF coil that stimulates your whole body. But let's go back to this simple case of just two coils. And so one thing you can do is you can take this coil. So you just take the signal from this coil, and this is done. And then you take the signal from this coil and just delay it by 1/4 of a cycle. So just insert an electronic delay, and then add them together. And I remember that when the physicist said, "Oh yeah, that's what we do. You just add them together." He said, like, "What? Why did you add them together? I thought they were sort of, isn't this a complex number? Shouldn't we keep them separate? And so why on earth would you want to do this?" But then after you've added them together, then what you do is you run it through the phase-sensitive detection. And then it makes a real and an imaginary. So this is actually done. Like, well, why the heck would you want to do this, or why would this work? And this is related to the signal to noise question. And the reason why this works, so you don't damage your signal in any way if you do this. You just take these two signals, you mix them together, which you would seem like you were sort of like losing something, and then you separate them back out into a sine and a cosine, basically. And why does this work? And the reason it works is because the noise that is picked up by this coil versus that coil is orthogonal or uncorrelated the same way. So noise is uncorrelated. And we would call that, orthogonal. But what does that mean? So what that means is that there's the signal you're trying to pick up, but then there's other things, radio waves in the environment, or your stomach. Your stomach has sort of got a bunch of atoms in it, and those atoms are wiggling, and they're generating radio waves. And that's noise. We don't want that. We just want to sort of pick up something that's in the head. But whatever stomach rumblings that this coil picks up, because this coil is at right angles to it, it won't appear in this coil at all. So the noise generated in these two coils is completely uncorrelated. And because of that, it's kind of safe to mix them together and then pull them apart again. So that was our first sort of strange result. So noise, in quadrature coils, that means like, off by 1/4 cycle. is uncorrelated. And so definitely it's advantageous, because it's uncorrelated, it's advantageous to have a second coil, because it's going to have, now, unfortunately, of course, if you make another coil on the other side of the head, its noise is going to be correlated with a vertical coil, if you put a vertical coil, so you only get 2 cracks at it. There's only 2 possible uncorrelated positions of the coil. But it makes sense. You basically get a square root of 2 improvement. In signal to noise, so it's like about 1.4 by using 2 coils instead of 1. So that's one important concept about signal to noise. You can have a coil that's at a different angle, and it can give you some additional information that's uncorrelated with the one information coming from the other coil. But that's not enough. So one big advantage is using a smaller coil. But now here's the issue. We're talking about radio waves, and so radio waves, they just kind of come out of the head and they go a long distance, like they go right across the bore, no problem. They go out into the room, come out of your head, and just like they go into the coil, but they go everywhere. And so if you think about that, what's the best way to record radio waves? Well, make a big antenna. And so it turns out the body coil is a nice honking big antenna. So here's the body coil. So here's your little head inside the the body coil. So the body coil is a great way to record radio waves. So why don't we use the body coil? And in fact, you can record from the body. You can use the body coil to stimulate RF, but you can record from the body coil. That's why it's called the body coil, because you can actually, if you want to record and make an image of the whole body. But it turns out it's not very good. The signal to noise isn't very good. And why is that? And so the reason is, it's a great antenna. It's a much better antenna than a smaller coil, like this. Like if you put a little small coil next to the head like that, this guy is going to actually be a better antenna. And why is it? Well, some radio waves came out of your head, and then you got this big antenna to pick them up, and it does a great job of picking them up. So if I want to test, did somebody leave a smartwatch somewhere in the MRI magnet? It's generating a bunch of noise inside the radio wave noise inside the MRI. I would use the body coil to try to diagnose that, because it's a big antenna. So why is a small coil better? And so the small coil is better because it has more trouble picking up noise from other part of your body. So there's the stomach again, and the stomach is making radio waves down here. The body coil is going to pick up those radio waves from the stomach, just from all the atoms, the rest of the atoms in your body that are wiggling and generating little radio waves. So there's going to be all this, because as long as you're not at absolute zero, all your atoms are massively just wiggling back and forth at many hundreds of miles an hour, just sort of just bouncing back and forth. And so the reason that a smaller coil is better is because it essentially can't see. You can sort of think of it as getting the same signal, signal as big coil, but it picks up less noise from elsewhere. So that's why everybody's moved to smaller coils. And so we have a 32 channel coil, a 64 channel coil. And all those coils, they're not all at right angles to each other. They generally, are sort of spaced around the head in this direction. But, if you look at an individual coil, it's about like this big, and the next one is just sort of, 20 degrees relative to that one. So they're not all, so the noise is not uncorrelated in all those coils. But the reason why you get a better signal to noise from it is because those coils are small enough that they don't pick up junk from other parts. But then it also matters, it actually does, even though I said it didn't over here, that it didn't matter how far away the coil was from your head, it does matter. Antennas and the electromagnetic theory of antennas is quite complicated. I don't understand it very well, but it is definitely true that there is some coupling between the coil that varies depending on how close you get to the head. And so close to the head is better. So you can actually get, so it's not quite the same signal, but it's almost the same signal. But if you close to the head will give you a better signal. There'll be more coupling between the radio waves as they go into the pickup coil. And this is actually quite striking. Like, so if you take a coil that's about like this big and put it over here versus like just putting it over here, or even just putting it like that versus that, you can almost double your signal. So you can actually double the signal to noise, not just square root of 2, like a full doubling, just by just taking the coil from here and putting it to here. So from the point of view of sort of MRI technology, there's still at least a doubling of signal available if somebody could sort of figure out a way to make a head coil that had a bunch of small coils that would be sort of adaptable, so you could put somebody. The problem is people's heads are all different shape, and so what they do is they make a hard head coil that will fit the 2 standard deviations beyond the average, maximum dimensions of a head. And so if you could somehow sort of make a coil that had, 128 channels in it, and that was flexible, and you could sort of like move it in right on the head so that it was close to the head, you could at least double, maybe even almost triple the signal. That would be like a 6 Tesla magnet just by having a better coil. So that's the reason people haven't done it so far. Is kind of hard because it's got gazillion parts in it, and you've got to somehow make sure you don't break any of the wires that are connecting up the, a flexible coil. But sooner or later, somebody's going to come up with a coil that can sort of fit right against the head, and that will there'll be another doubling or tripling of the signal. You can use it to increase your spatial resolution. So that's just like a crude overview of some of the signal-to-noise issues. So you could have different angle coils, but there's only 2 angles basically available. You can have a smaller coil that picks up less junk from your stomach and the whole rest of your body and the lights in the room. But then you can also put it closer to the head, so it couples better with the head. And close is really good. And if you do animal experiments, people actually implant a coil. So the absolute best thing would be to get a head piercing, skull piercing, and get a coil. If you had a coil that's right touching the brain, boy, that's a really good coil. It only just picks up from that little piece of the brain. You can get much higher resolution that way. But don't do this at home. Yes. Okay. Any last questions about the RF coil, about the phase-sensitive detection, which is how we implement the rotating coordinate system? And essentially how we implement the popular signal equation that we heard about last time, and then signal to noise. Okay, so next time we'll go over what happens when you got multiple frequencies coming in, which there are. So like there's different parts of the head and they're oscillating at different frequencies, and we have to deal with multiple frequencies. So that's Wednesday.